So today's video is introducing how to measure ground reaction forces with a force plate. This is a quick orientation to the force plate just to get you prepared. So this is our force plate that's embedded in the lab. You can see here it's just got some vinyl covering it. Doesn't look like much, but you can see the outline and the border of it. So this will come in handy later, but I know from the way we've set up the lab that the cables entering the force plate enter right there by my right foot. So using the right hand rule, where you stick out your index finger, middle finger, and thumb to define the three axes Fx, Fz, and Fy. Your thumb indicates Fx, your index finger Fy, and your middle finger facing down is Fz. This is then anchored to that reference point of the cables entering the force plate. Almost every force plate works like this. So if I position my axis system there, I now know where my reference points for positive Fx, pointing towards the side of the room, is. And just before I demonstrate that by kicking on the plate to show you the shear force, I'll get you oriented to what our collection program here looks like. So if we have our 6 lines on the top screen, we have 3. The top one, number 1 being Fx, number 2 Fy, and number 3 Fz. And then on the bottom display, Mx, My, and Mz, or our moments, which I'll get to in a minute. So relating these back to the plate, using that axis system, we can see that our top line, Fx, is our shear force, and when I kicked towards the side of the room, that top line, you can see positive deflections. If I kick towards the front of the room, or positive Fy, you can see 2 positive deflections in specifically Fy, and then stomping in Fz. You'll notice that all 3 had positive deflections in Fz. That's because I have to put force down in order to create that shear force. But you'll notice if I kick the other way, I can create a negative Fx shear force. And if I pull back on my heel, I'm creating a negative Fy shear force as well. I would need a suction cup or something to pull up on the plate to get a negative Fz. So now for the explanation of those bottom 3 traces are moments. Moments are the rotation about those axes. So for my thumb, my Fx, I would have clockwise rotation around that axis if there was a line running straight through my thumb. For my index finger, my Fy, clockwise rotation around it that way, and Fz, that pivot around. Using my axis systems here, it's a little bit clearer. So that clockwise rotation around the X, clockwise rotation around the Y, and then clockwise rotation around the Z axis, and what those positive moments will look like. So if I stomp at the front of the plate there, that will rotate it clockwise around, and you can see the positive deflection on my 4th trace, positive Mx. If I stomp to the left side, that will create a positive rotation around the green Fy. So you can see on the 5th trace there, the positive My rotation. And if I create a rotational shear force around that Fz vector, you can see that I create an Mz moment in the bottom, on the bottom of the 6th trace. So what we're going to do now is look at some example recordings when they're generated by humans and what those would look like. So if I start my trial here, I then 0 the plate. And when you have somebody step on the plate, the Fz will jump up, and that's that person's, essentially their body weight being accelerated by gravity and the ground reaction force that accommodates that. And then they step off the plate, it returns to baseline. This is what that sort of looks like in practice. This is what the quiet stance or baseline trial is. I start the trial here. We have a hard 0 on this plate, so I 0 the plate from the amp. I ask my participant Ian here to step on the plate, and he stands quietly. And then this is what that's going to look like when I overlay the 2. I have Ian step on. You can see that the Fz increases, and you pretty much have a really accurate body weight. He steps off, FZ returns to baseline. You can see that we had some moments in the bottom trace if we watch it again. And those will simply be from him stepping off axes, not directly on the center of the plate through which those axes flow, and obviously creating rotational moments around those. Okay, so the next one we're going to take a look at is a vertical jump with counter movement. So if I zero the plate here, I have Ian step on, and I have him perform a normal jump, jumping straight up and landing back down on the plate. If we take a look at the forces, we'll see what we can see here. So you can see FZ increase as he steps on. And then as he begins to perform the counter movement, you can see a dip in FZ before a large increase in which he starts exerting for a lot more force down. So pushing off with his legs. You see a brief period of time where he's in the air, the force drops back down to 0, and then a really high impact peak as he lands back on the plate. We're going to do our broad jump, our short one here. So this profile, especially in FZ, should look fairly similar, except without the landing. So the starting phase should look fairly similar. He's performing a slight counter movement and jumping forward. So FZ, we expect the first half to look a lot like the vertical jump. He steps on here. We can see the decrease in the counter movement and then the increase. So the propulsion phase as he jumps off. Obviously he's not landing back on the plate, so you don't get that landing impact peak in FZ. But what we also can see if we watch it again here is we get some negative FY forces. So those shear forces as he pushes backwards. Now it was a short one, so what we should see is when we move into the medium broad jump and especially the long broad jump, we should see that those FZ profiles look fairly similar. Maybe a little bit more force in the propulsion phase is needed as he needs to go a little bit higher to travel longer. But what we're going to see is actually a lot of that force get translated into the negative FY. So we should see a larger and larger deflection in FY. So almost twice as big there as the medium one. And then if we're going into the long one here shortly, we should see that FY negative force continue to increase. All right, and finally the long, we should have pretty much an exceptionally large FY shear force here as Ian uses the friction with the ground and his shoes to propel himself forward. He's creating a ground reaction force that is equally pushing back towards his feet as he jumps forward. So if we now take a look at the FY, again, FZ should be fairly similar, maybe a little bit more force in the propulsion phase. Yeah, a little bit more, but our FY is almost 3 or 4 times as big as that first short broad jump. Okay, moving away from the broad jumps here, so not quite as interested in our shear forces, we're going to take a look at a couple of different drop jumps. The first one with a harsh landing and the second with a more gentle or more absorbative landing. So the first one, I have Ian jump off this box here and land fairly straight-legged, don't want to hurt himself. And we'll take a look at what we can see here and then compare it to one where he tries to absorb the landing a little bit more. Particularly, we're going to be looking at FZ here, so that third trace, really high impact peak, actually completely overlaps with our second trace, or our FY, so it kind of obscures it. But when we look at the data, we'll be able to see it a little bit better. So taking note during these that almost none of that force is being distributed over a large amount of time. The impact peak is indicative that a lot of the force is occurring almost all at once and transferring through all of Ian's joints all the way up the chain. Whereas if he goes to absorb that a little bit more with some of the musculature and by moving his joints and slowing his momentum down onto the plate in this sort of soft landing one, what we should be able to see when we take a look at the data is that that impact peak isn't quite as high in FZ, and it's actually the same amount of force just spread out over a longer period. So we'll have to take a look at the data and see. Again, it's right up into the FY range and definitely a little obscured. So when we take a look at it again, all we can see is that it's sort of equally high to the first one, but we'll take a look at the data and see what that shows. Okay, finally on to our center of pressure measurement. We're going to run a couple of different trials here and see how that center of pressure reacts as it tries to stabilize his center of mass, and he applies forces around the edges of his feet. First trial is going to be regular dual stance. We're just going to have Ian stand on the plate. These aren't that exciting to watch, but it'll be interesting to take a look at the data and compare our regular dual stance. So this is again kind of a baseline to our then eyes closed and our single leg eyes open and eyes closed. So we've got about 10 seconds of data there. So if we flip back and we show the screen view again, what we can see here is that Ian is on the plate the whole time, so there's no distinct increase, but we have very, very minor fluctuations in our forces, and now we can start to look at the center of pressure trace on the right above where the video of Ian and I is. And so you can see that little spaghetti plot, or the center of pressure, move around over time. It's fairly tight, and he controls it fairly well in one specific area. So when we flip over here to our dual stance eyes closed and have Ian rely solely on proprioceptive and vestibular inputs, no longer having those visual cues in order to aid his balance, what we should see is slightly more variation in that center pressure trace, and we'll see if that shows up and he's not quite as well able to control his center of mass as it moves around. Taking a look at the data, we can see that the trace is actually fairly tight and well controlled in the center there. We have some slight medial lateral deviations that are increasing, but one of the measures that we might want to take a look at here is actually the velocity of that trace. So is it moving around at a higher frequency? The amplitude might not be as large, so the trace might look exactly like it did before, but it might be moving at a higher frequency, and we can take a look at the data then. Now this won't be directly comparable to the dual stance, but looking at single leg stance is interesting because now you've taken out some of the accommodating measures that the other leg can provide. So if we have Ian stand on one leg with his eyes open, and he's got it back. So what we can do is take a look and see if he's able to control his center of pressure a little bit better with his eyes open than he is with his eyes closed. So finally, we're going to compare this to eyes closed, keeping a note on what our plot looks like there. So off to one side, obviously under 1 foot, but fairly similar in the medial lateral and anterior posterior directions. Definitely not the tightest trace, and when we get Ian with his eyes closed, you can see he's having a lot of trouble now, having very little accommodating from the other limb, and no visual input, only relying on vestibular and proprioceptive inputs. Alright, we'll see if we can see absolutely anything in that trace, so this will be fun. Okay, you can immediately see that the center of pressure trace is all over the place, and obviously as he uses his other foot touching off the plate, it's actually aiding a little bit and not giving us completely where that center of mass would have fallen, completely outside the border of that foot. You can see the rotational, the moments around on the bottom trace absolutely bouncing all over the place as he struggles to keep balance. So what we'll do now is we'll flip into that analysis and start taking a look at some of this data.